Hello everyone, my name is Shaoxiong Ye from Southeast University. Today, I would like to speak about in situ observation of tricalcium aluminate dissolution in water. Minor dissolution is central to numerous geochemical reactions and environmental processes. For botany cement, it has been well known that the dissolution of aluminate phases plays an important role in controlling the overall hydration process and the early age properties development. Despite many remarkable efforts had been spent on understanding the reaction kinetics of cement, the lack of knowledge on situ dissolution kinetics is a remaining challenge due to extremely high reactivity. Normally, the dissolution and precipitation are always coupled together like twins, making it difficult to study situ dissolution alone. Fortunately, with the development of holography, we are able to catch the initial time window of pure dissolution of situ. Holography is the science and practice of making holograms, and is common in our daily life. A dancing performance at Chinese New Year in 2015 is a good example. In this work, we used digital holography microscopy (DHM) to observe the dissolution behavior of situ in water. Specifically, a hologram of water-mirror interface is captured by the laser interference and by using the Color software. The 3D structure of the interface can be reconstructed. In other words, one hologram contains the whole information necessary to reconstruct 3D information, and DHM has an ability to capture maximum more than 100 holograms per second. So, DHM is suitable for constructing 4D measurements, 3D topography, and timescale, such as membrane deformation, electrochemical etching, and water evaporation. In our lab, the DHM is connected with a fluorescent cell to construct dissolution experiments, and this upper left picture shows the whole platform in our lab. Water is pumping into the fluorescent cell to flow past the situ surface, and the flowing rate of water is regulated by this pump. Cubic situ pellets are produced by hot press sintering. Simply, situ powder is molded in a vat and is sintered according to this procedure, as shown in this picture. The maximum sintering temperature is 1250 degrees centigrade, and the maximum applied pressure is 40 megapascal. After the sintering, situ is carefully polished to obtain the dense, smooth pellets. It's well known that the grain size significantly affects the minor dissolution rate, and the prepared situ here has a grain size of about 18.9 micrometer. Before the dissolution experiments, situ pellets are partially coated with inert platinum as a reference plant. When situ dissolves, the surface height will reduce, and its dissolution rate can be calculated according to this equation. In 2017, Brent and Burrer had used the DHM to obtain situ dissolution rates in water alcohol solutions and predicted its dissolution rate in pure water. However, due to the extremely high reactivity, to our best of knowledge, the experimentally obtained dissolution rate of C3H in water is still missing. Thanks to DHM, we are able to capture the short-time window of C3H dissolution. In water with different falling rates, C3H progresses through 3 stages within the first 3.5 seconds. The 3 stages are distinguished according to the slope of surface height change. The rates within the initial 0.5 seconds are independent of the flowing rate, probably because the extremely short time period is not long enough for mass transport to influence the rate or to cause any precipitation. In other words, we successfully captured the rate dissolution rate of C3H, and the calculated dissolution rate is about 1 millimole per square meter per second, and this value is much larger than common mirrors, about 1,000 times larger than gypsum, 10,000 times larger than CAS, and 1,000 times larger than the value predicted by Brent and Burer's work. The C3H surface morphology changes dramatically during the initial dissolution stage. We also used atomic force microscopy to monitor this change. It can be seen that the pristine C3H surface is smooth, and HP typically triangular in shape, formed immediately after contacting with water. The density and the size of these peaks could withstand. After the first stage, precipitation of products occurs and the surface height change rate is modified. We also characterize the products. After contacting with water for 3 seconds, a layer of about 300 nanometer thick product forms, and the product is with the foil shape. We also used glancing incidence X-ray diffraction (GIXRD) to characterize the crystal structure of the hydrogen product. The new peak formed at 2 theta between 11 degrees and 12 degrees proves the formation of calcium aluminate hydride. Based on the above results, we propose a simple model to expand the rate controlling mechanism of C3H dissolution. Initially, the solid dissolves to release ions into the solution and the H peaks form. At this stage, the solution is still undersaturated with respect to product phase. Then, within a very short period of time, a layer of foil-shaped calcium aluminate hydride rapidly forms on the C3H surface. Due to its the incomplete coverage and the porous nature of the hydrogen product can limit but not completely cut off access to water. This produces a static media overall dissolution, and at this time, ion diffusion also can affect the dissolution rate. So, the following conclusions of C3H dissolution in water can be drawn. I want to emphasize that situ dissolves rapidly and the true dissolution rate is about 1 millimole per square meter per second. And diagram provides an appealing way to check the dissolution kinetics of reactive minerals. Thank you for your listening.